The last violation of Hardy-Weinberg equilibrium conditions that we'll discuss in this course is the case where mutation and selection are acting in opposition to one another. So mutation is simply the production of new alleles, say a wild-type big A allele being converted through a mutation event to a little a allele. The rate at which that happens is denoted with the Greek letter mu. So as chromosomes are replicated, each individual locus has a certain probability of a mutation event to convert it from one allele to another, and we can describe that rate or that frequency with mu as a rate. Now let's also consider the case where selection is acting. So if we have heterozygotes that breed with one another to produce little a individuals, we could hypothesize, say in this population, that this genotype has a fitness of 0. Another way to put this is to say that the selection against this genotype is 1 or absolute. So this genotype is not capable of reproducing in this environment for whatever reason. Perhaps it's due to survival, perhaps it's a sterile genotype. All that matters is that we say the fitness is 0, meaning that the selection is 1. Something to consider now is we have two forces. We have mutation, which is putting new little a alleles into the population, and we also have selection. Because it is removing specifically this genotype, we could say what the fitness of the heterozygote is 1, and say the homozygous wild type or homozygous dominant also has a fitness of 1. So these do not have any selection acting against them, but the little a genotype is fully selected against. So we have opposing forces. We have mutation, which is producing new little a alleles, and we also have selection, which is removing little a alleles from the population. Now, the frequency by which this happens, that we have a mating where we have two heterozygotes coming together to produce a little a individual, well, the probability of that is dependent on this rate here, because this rate influences the frequency of this allele in the population. And the frequency of this allele in the population determines the frequency of heterozygous individuals, which is necessary to produce little a individuals, which then will be selected against. Put another way, the forward mutation rate and the rate at which individuals are removed from the population through selection, these rates are related to one another. So because these two rates are related, we can use an analogy to describe this population. Let's imagine this population as if it were a barrel with a hole at the bottom that allows water to drip out. And then we have a pipe that's producing, water dripping in. What happens here is you're going to have an equilibrium value because the height of the water determines how fast the water is dripping out. And how fast the water is dripping out is also dependent on the input rate. So this is a related rate such that there will be an equilibrium value. We can model this equilibrium of the water level as the equilibrium value for Q, which is the frequency of the little a allele in the population. Because it's an equilibrium value for Q, it's established over time, we'll signify that it's an equilibrium value by giving it a little hat on top of it. So this value, Q with this little hat over top, is indicating that it's an equilibrium value for Q. Okay, obviously the height of the water in the barrel is going to depend on two things. It's going to depend on how fast water is coming into the barrel, which we said is our mutation rate, or mu, that's kicking in new little a alleles. And it's also going to depend on how fast little a alleles are leaving. So this is going to be dependent on the selection. Now, we can model this with selection that's other than 1, so fitnesses that are greater than 0. But to simplify the math in this case, as we'll see in a moment, it's easier to model it where it's a full selection and there's a fitness of 0. So the equilibrium value for Q is given by a mathematical formula. It's the square root of mu divided by the selection. Okay, so let's use this equation and show an example of how we can calculate a mutation frequency for a recessive condition. based on knowing its fitness and also the incidence of that condition in a population. So let's examine an autosomal recessive condition. We'll just call it little a, and we'll say that it has a fitness equal to 0, so the selection is 1. Okay, so this is a condition that does not reproduce for some whatever reason. Perhaps it's a sterile or has other developmental issues so that reproduction is not possible. Okay, let's also say that it has an incidence in a certain population of 1 in 3,500 births. Okay, so based on this information, it has this incidence of 1 in 3,500 births, and you know its fitness. From that, we can calculate a mu value, and I'll walk you through how that's done now. So the first thing to recognize is that in this population, there are no reproducing little a individuals. So this 1 in 3,500 births that have the little a genotype are strictly arising from pairings of heterozygotes to produce little a individuals. What we're interested in finding first off is what is the frequency of the heterozygous class. We already know in this population that the frequency of the homozygous recessive class in any given generation is 1 in 3,500. We might also observe that this is a constant frequency in this population, generation to generation. So this is a population that is in equilibrium because it's consistently producing 1 in 3,500 births with this condition, and that's due to this balance between mutation and selection that we're working on. So we might ask ourselves, well, what are the requirements to have an individual that is little a? Well, we need a heterozygous mother and a heterozygous father, and 1/4 of those children on average will be little a. So put another way, we could say that 1/4 times the probability of being a carrier times the probability of being a carrier is equal to 1 in 3,500. Now it's simple algebra simply to rearrange this and solve for the probability of being a carrier. So the probability of being a carrier to the second power is equal to 4 divided by 3,500. So I've just multiplied both sides by 4. And now all we need to do is take the square root. So the probability of being a carrier is equal to the root of 4 divided by 3,500. So if you get out your calculator and give this a check, it should come out to approximately 0.034, approximately. Again, rounding is going to be an issue. So the frequency, put another way, the frequency of the heterozygous state in this population is about 3%. Okay, now that we've calculated the frequency of the heterozygous class by using that logic that infers backwards from this incidence of the little a genotype, we now have what we need in order to calculate Q. So Q is equal to the frequency of the little a class plus 1/2 of the frequency of the heterozygous class, which in this case is 1 in 3,500 plus approximately 0.034 times 1/2. So that is going to be approximately 0.017, and we'll add those together. And if you do your math and check it out, it should be approximately 0.0173. Obviously, this is going to be a very small value, so it doesn't add very much to this value for the heterozygous class. So if that's Q, and remember, because it's Q in a population that hasn't changed for many generations in terms of its incidence frequency, we know that this is the equilibrium value for Q. So now that we know the equilibrium value for Q, it's a simple step to calculate the equilibrium value for P. It's simply 1 minus the equilibrium value for Q, which is equal to 0.9827. So now we have our equilibrium value for P and we have our equilibrium value for Q. And now the next step is to take this and plug it into this equation in order to figure out what mu is, because now we have everything that we need. Okay, now that we have our equilibrium value for Q calculated, we can now use it with this equation here. So in this case, because our fitness of this genotype is 0, as we discussed before, this equation reduces down to simply the root of mu. So if decimal 0.173 is equal to the root of the mutation frequency, then simply squaring both sides of the equation will give us our value for mu. So if you punch that into your calculator, you should come up with approximately 3 times 10 to the minus 4, plus or minus. It's depending on if you've got rounding errors that you've carried through. It should be approximately 3 times 10 to the minus 4. Now, 3 times 10 to the minus 4 is our mutation frequency. That's the frequency in this population, or the probability, we could say, that this particular locus is converted from a big A to a little a during chromosome replication. This is the frequency at which new little a alleles are entering the population, which, balanced by the selection of removing little a individuals from the population over time, is what brings this population to its equilibrium value for Q. Now, one extension of this type of work that you'll see, and we'll do some practice problems in class on this, is this type of analysis allows us to determine the frequency of rare genotypes in a population. So previously in pedigrees, we've often made an assumption, if it was a rare genotype, that the probability of somebody marrying in to a family carrying that rare allele, we often assumed that that probability was 0. If you have this type of information, however, you can now calculate the actual probability that they're marrying in as a carrier. So for example, in this particular case, instead of 0, we now know in this particular population, for this particular condition, the probability of finding someone who is heterozygous in this population has a non-zero probability. So in a pedigree, we would need to factor this in. We can't now assume that they're big A marrying in. The probability that they're big A is a certain value, and the probability that they're heterozygote is this value. So we'll do some examples of that in class.